of conservation, which says that in isolated system, no external force, meaning that isolated system means that no external force. So the total momentum before the interaction equals total momentum after the action, after the interaction. Assuming two balls is being heated together, you hit two balls. So before you hit the ball, one is coming this side and the other one is coming the other side. Before the ball hits each other, so they will have a mass, which is the mass 1 and a initial velocity u1. The second one also will have mass 2 and the initial velocity u2. Now after their collision or their interaction, they will now be having another new velocity. The mass is still there, but a v1, a new velocity, and the second mass is still there, a v2, which is another velocity. So meaning that the total momentum after the interaction is equal to total momentum before the interaction, and this holds for all types of what? All types of collision. Now from there we can now look at different type of collision that we actually have, since we say this holds for all type of collision. Now let's start. The first type of collision we have is elastic collision. In an elastic collision, the momentum is conserved. So that means the momentum is conserved, which is always conserved. Let me say so. Now the kinetic energy is also conserved here. Example, we have the billiard board. 2, we have the gas molecule. Let's take an example, this gas molecule. We know that the gas molecule are in dispersed form, or what will I say? They are in scattered form. So they will always collide with each other and bounce back. So they collide with each other and bounce back. So this is an example of a elastic collision. Now let's talk about the inelastic collision. We have this inelastic collision. What we should know is that one, the momentum is also conserved, and the kinetic energy here is not conserved, because some of the kinetic energy is converted to what? Heat, sound and stuff. So it's converted to other form of energy. So the kinetic energy here will not be conserved. Example, let's talk about this clay ball sticking together. So clay ball now sticking together. So the kinetic energy before sticking is not equal to the kinetic energy after sticking. You can see. Now we go to the another type, which is perfectly elastic collision. These two bodies stick together after collision and move as one mass. So the first one is coming, the second one is coming. Now they hit each other and they stick together, now moving as one mass after the collision. So this is a perfectly inelastic collision. So here also the momentum is conserved. You can see the rule said it holds for all the type of collision. You can see all of them, the momentum is what? Is conserved. But note, the momentum is conserved, but maximum kinetic energy loss occur, because when it stick together, the kinetic energy, maybe assume is around 100 joule before, it may go down to as low as maybe 1 joule, so that it will not even be moved. The body will not be even moving a reasonable like the kinetic energy will not even be reasonable anymore. So it will almost be like the thing is stopping, is going to rest. Okay, so that's what it means that maximum loss of kinetic energy actually occur here. So here are other cases of momentum that we actually need to take a look at, that is going to be of beneficial to us. So one, we have the recoil of a gun. So when a bullet is fired, the gun recoil backward due to the conservation of the momentum. Now let me try and explain this. What it's trying to mean is that when you actually fired a gun, the bullet moves forward, but the gun himself moves backward. So it recoils backward. So meaning that as the bullet is moving forward, the other body, let's take the coil as the first body. You know, we are talking about two body colliding. The first body is the bullet, while the second body is the gun himself. Now, before the collision is 0 because they are not moving already. Now after the collision now, the that of the gun moves forward, while that of the bullet, the gun moves backward, while that of the bullet moves forward. So now it now said when the bullet is fired, the gun recoil backward. That means it goes backward due to conservation of momentum. So here means that m1u1 plus m2u2, which equals to m1v1 plus m2v2, the normal momentum formulas. Here we already know that this one becomes 0 because the initial, there's nothing initial there. The initial velocity is, the thing is from rest, the gun is from rest. So the only thing we can see is just the final stuff. So that means this side is already gone. So now it will now be the gun will be minus that of the momentum of the gun will be minus that of the bullet, because if the gun is going forward, the bullet will be going backward. So or the minus of the minus momentum of the gun is equals to positive value of that of the bullet. So meaning that m gun v gun is equals to minus m bullet v bullet. Please let's take note of this. Is a special case of momentum. Okay, another case is that of explosion. So in an explosion, the internal force push apart. Is that in an explosion the internal force push part apart. So like it's scattered over two. So the internal force, sorry for that. So the internal force, like the thing wants to blow. Let me see that too. Sorry for the Yoruba aspect. I'm a Yoruba guy, so it's normal. So in an explosion, the internal force push the part apart. So the total momentum of all parts remains zero if no external force act on it. Meaning that in that explosion, when the thing is about to burst, so the total momentum will remain zero. The total momentum will remain zero. As far as there's no external force acting on it. There's no external force acting on that body undergoing that explosion. So in that explosion, the direction energy, the total internal momentum of all the parts will remain zero if there's no external force act on it. So we should need to take note of this because there are some little special case of momentum and collision, so that we actually need to take note of. Okay.